Hello and welcome again to my Physics Online video lecture series. In today's video, I want to talk about density. So this is going to be a short video in which we discuss material density, and that's about it. However, it is a video that will be built upon in our future discussions of fluids, both dynamics and statics, so making sure that we understand what density is kind of an important introductory video to this section. So density we represent usually with the Greek letter rho, or at least I represent it with the Greek letter rho, and a lot of textbooks do as well. It is defined as follows. The density, unless it's modified by some modifier like charge density or population density or whatever, the density as such is generally defined as the amount of mass divided by the volume for a subject. So a high density object has a lot of mass per unit volume. A low density object has very little mass per unit volume. So density, again, is mass per unit volume. And that is, in some sense, it for defining density. Now, how is it actually determined? Well, it depends upon your context. Generally speaking, what we do is we take a material and we take different samples of that material and we measure the mass and we measure the volume that they take up. And we generally assume single materials, but you can do it for varied materials. One of the assumptions that we are going to be making is that the density of our object remains constant. So this is for a given object, and by object we mean like substance. Now, this is not a generally valid thing. So things for which that is not valid at all, compressible gas, so most gases, most plasmas, most Bose-Einstein condensates, so gas, plasma, etc. That's not valid. So this is not a valid assumption if we're talking about those. And actually, even for solids and liquids, the density is only mostly constant. So solids, liquids, we might say like an ideal fluid or an ideal solid or an ideal liquid, but these are a little compressible. Basically, you're talking parts per thousand at the most, but mostly like tens of parts per million. So we might say like ppm levels. So if you're going out to 6 significant figures with these calculations, then yeah, the density varies, but as long as you're looking at like 2 or 3 or even 4 significant figures, the density is more or less constant for these things. Also, there's temperature change. So temperature effects, especially solids, can expand. So this is expand, contract. This would be not valid or invalid for this assumption. Okay, so as long as we neglect this, and we don't need to go out to like 6 significant figures for these, density being constant is an okay assumption. So how is density measured? What would be one way of measuring it? Well, you could, in principle, take different objects of the same substance and measure mass and measure volume. And if you do that, and you made a plot, and on one axis you put the volume, so volume down here, on the other axis you put the mass, you would end up getting something like this. So this right here might represent, let's say, I don't know, iron or something. Maybe for some other material, maybe you end up getting more like this, where you've got more mass per unit volume. So this could be maybe like copper, Cu. Both of these should go through the 0, 0 point, by the way. Well, in both cases, we can say that slope of the line is the substance density. And copper is generally more dense than iron, as it turns out. Gold is more dense than copper, etc. This may be a little exaggerated, by the way. Copper is not like 2 times more dense than iron, but it is denser. So this is one way of going about getting the measurement, and the fact that all the points are on the same line, more or less, that is an indicator that the density remains constant as a function of volume, or as a function of mass. So that's sort of like the main point that needs to be driven home. What about units? Units of density. So there are several units that are in common use. For metric system, you have various types of centimeter, gram, second units. These usually are in grams per centimeter cubed. This is the same thing as grams per cc. So cc stands for cubic centimeter. The MKS unit, the standard unit that you would want to convert it to if you want to end up calculating something from it, like pressure in pascals or weight in newtons or whatever, is you need to go to kilograms per meter cubed. The conversion factor is that 1 kilogram per meter cubed is equal to 1,000 grams, or G, per centimeter cubed. Okay, and now another set of units that are still metric but not really belonging quite to this or to this. So we could say like other metric. There's kilograms per liter, and then there's also grams per milliliter. And the conversion is, this one is kind of like quasi-CGS because 1 gram per milliliter is the same thing as 1 gram per cubic centimeter. So 1 milliliter is a cubic centimeter. 1 ml equals 1 cm cubed. This also means that 1 kilogram per liter is the same as 1 gram per milliliter. And so this unit right here is equivalent to grams per centimeter cubed. It follows that, among other things, there are 1,000 kilograms per liter to equal 1 kilogram per cubic meter. So that's a bunch of different unit conversions that you might do. Okay. What about substances that are not one atom only? So we could call them like mixed or compound substance. So mixed or compound substances. Well, these are going to be a little bit different. So if it is a uniform mixture, essentially like an aqueous solution or something like that, then both of these get to behave, this behaves as pure substance. So pure substance. Put differently, water, H2O, has we could say, constant density of about 1 gram per milliliter, in the liquid stage, anywhere around room temperature, down to 4 degrees C, down to even 0 degrees C. So those are compounds. If you have a mixture, you can have a uniform mixture, so uniform or homogeneous. So this would be like a solution, salt in water. And salt in water kind of depends, but like salt water from the ocean, for example, if you sample from the top of the ocean, you get about, let's say, 1.025 grams per milliliter top of ocean. That's very nearly, though not exactly, constant. It should be constant for a given region of the ocean, though. A given, like, sector within, 10 meters or 100 meters or even a kilometer or whatever. So if you have a non-uniform, like a heterogeneous mixture, then your density will tend to not follow this constant density. So this one would be not constant, and or not constant density. And so examples of this would be like sand. Now sand in bulk may act like a constant density, but there's sort of like space between the sand particles or dirt or whatever. There's space between the dirt particles that could be filled by air or water or what have you. Another example would be like pumice. So that's like the rock that you get out of volcanoes, like lava rock, where there's all those little holes throughout it. And if you break a piece of pumice off of a larger piece, the densities may be different because you have, in some sense, a heterogeneous mixture of whatever the pumice rock material is and the air. So that's different densities. I guess we could do a quick example to close things out. So for example, we have aluminum. It has a density of 2.7 grams per milliliter. So rho is 2.7. This is rho. This right here is your volume. We know that the density should be mass divided by volume. So if what we want to do is find the mass, we just rearrange the equation to say that mass is density times volume. And so that would be 2.7 grams per milliliter times 1 kilogram per liter by or over or per gram per milliliter times 4.2 liters. If you multiply those two together, you get that the mass is about 11.34 kilograms, and so if we round it to 2 sig figs, this would be about 11 kilograms of aluminum. That's all for today. Thanks for watching, and I hope you enjoyed it.